Okay, well, hello everyone. This is going to be an interesting experiment. It seems kind of strange without any audio feedback, but it looks like it's going to be fun. So, I'm a research astronomer at the University of Hawaii. I'm a tenured faculty member, equivalent to full professor. But I think you want to know how I get started in astrobiology or planetary science. So let me start at the beginning. When I was about 7 years old, Star Trek came out, and I found this absolutely fascinating, and we'd watch it once a week whenever it came on. And so at that point, at age 7, I said I was going to become an astronaut or do something related to space. And, growing up, I used to sleep outside in the backyard camping with my dad, and I got very interested in the stars. I hadn't yet selected which area of astronomy might be of interest, but I do remember middle school, there was a month in January when we got snowed in and there was a teacher strike. So I decided I would start my astronomy astronaut career at that point, and I started to read Encyclopedia Britannica and took notes. Well, it turns out taking notes in a field that's way too advanced for you meant you're effectively copying Encyclopedia Britannica. And I happened to start with stellar structure, so maybe that's why I did not go into stellar astronomy. So my parents were encouraging, but tried to tell me that maybe I should wait and decide if I liked physics before setting out on this career path. I have a bit of a stubborn streak and figured I'm going to like physics, so I'm just going to go through this and tell them I like it no matter what. I didn't actually like physics in high school, and in terms of education and outreach, I really think they had to start with light and radiation instead of frictionless slabs sliding down inclined planes, because frankly that wasn't too interesting. But I stuck with it and ended up getting a PhD in planetary science after a undergraduate degree in space physics. What was fun was I'd taken a lot of advanced placement courses in high school, so when I got to college, I could branch out with some fun physics, and so I took space exploration and got pretty interested in aspects that were to become related to astrobiology. So I decided to take a year off between undergraduate and graduate school. I applied to observatories all over the world, and much to my dismay, nobody wanted anyone with just an undergraduate degree. I actually recently encountered all those rejection letters from some pretty famous astronomers, and I felt like I should make a bulletin board and frame them. But I did get an opportunity with the American Association of Variable Star Observers for half-time position and to work with Jim Elliott at MIT on planetary. And it was there I decided that planetary science was probably the route to go, and ended up doing a PhD in comets and investigation of their activity. That has continued. After I got my degree, I came straight to the University of Hawaii, where I got a faculty position, and I really continued to study the comets and what they could tell us about the early solar system. And in particular, I've kept that thread of observations going where you look at comets and watch when they become active, what this is telling you about their chemistry, because these are the leftover building blocks of how our solar system was put together. And then about 12 years, no, maybe 15 years ago now, when the Astrobiology Institute was first being assembled, one of the young researchers at UH said, hey, we ought to become a team. And she put in a proposal that was related to cosmochemistry, looking at meteorites. And so I joined her team, but we didn't really understand what the whole astrobiology scene was about, and we were not selected. And then when the CAM 3 opportunity came along, we decided to go after a theme of water and sort of a watery Drake equation, looking at the role comets played in delivering water to Earth, the way in which water formation occurs in space, and the water-rock interaction, and water and life. And so that's how I got sort of channeled my comet interests into astrobiology, and it's been absolutely fascinating ever since. As you study at the undergraduate level, the graduate level, you get your first job, you feel like you're getting ever more specialized, and it's funneling down to a narrow specialty. But with astrobiology, I feel I'm taking this and opening the funnel. It's been fun because I get to learn geology, geochemistry, geophysics, a little bit of chemistry, some biology, and so I have really enjoyed the astrobiology aspect of things. And what's really neat is this is leading now. I've gotten into various space missions, purely cometary, but now we're developing an astrobiology space mission to look at how the solar system distributed its volatiles in the early part of the solar system and leading to how Earth got its water. So that more or less gives you a quick nutshell of how I got here and what some of my research interests are. I've been involved with Deep Impact, Epoxy, Stardust Next missions, and provided some advice to several others, including Rosetta. So I'm certainly open for questions. I'm keenly interested in education and outreach along with the astrobiology research component of things. The question from Sanjoy is, what do I feel about deep impact in terms of damaging the object? That's an interesting question, and I ran across it in a major way in a teacher workshop I was running in about probably 2002. This was our TOPS workshop, Towards Other Planetary Systems, where we had 50 high school students and teachers for 3 weeks, and we ran sessions from 8 in the morning till midnight every day. One component of that workshop was dealing with archaeoastronomy, looking at ancient cultures and their astronomy. And to that end, we had invited a Native American Lakota Sioux chief to be part of that, to share some of the astronomy of his people. Now, he arrived a couple days early, and so he ended up sitting in on some of the comet lectures. And I happened to be talking about the Deep Impact mission, and we talked about, at that point I used the analogy of what a comet nucleus looks like. I said it looks like a potato. And so I finished the comet lecture, and it was the question period, and this Native American got up and said, well, his people didn't feel that comets looked like potatoes. In fact, they were sacred objects, and how could we do something like damaging the comet by hitting it? So this kind of derailed the entire discussion, and in fact, he got up and said, well, one of the ways in which his people resolve conflict is by having a talking circle. So we decided we better try this out. We completely derailed the whole afternoon hands-on activities and had a talking circle, which means that the two people with the differing opinions sit in the middle. They get to say each of their sides for however long it takes, and the Lakota Sioux chief took about an hour. And then I got to say my piece, and then everybody in the room that are sitting in a circle can comment on it. And he had brought up many cultural issues about how they've lost some of their heritage and culture because people have stolen their artifacts. So I used this as an excuse to talk about deep impact in the same way. I said that we've lost our information and culture and heritage about the early solar system because we don't have the information that we need to unravel our history. And so by hitting the comet, we were effectively not doing much damage. We were doing no different damage from what the natural world does through impacts, and it was more like a medical sample to get back at our early solar system history. This whole event took about 5 hours, but in the end, they were very satisfied that their sacred objects were being respected and that we were just going after our history like they were trying to recover some of their lost culture. Well, a question from Kara is about what are my thoughts on comets delivering water to the terrestrial planets in the early solar system. Well, obviously it's intensely interesting to me because we're trying to develop a $500 million Discovery class mission to address some of these issues. I think comets almost certainly contributed to water. The big question is, where did the bulk of Earth's water come from? Was it asteroidal? Was it cometary? Was it composed of gases that were just in the protosolar nebula at the distance at which the Earth formed? I suspect the answer will be that it was a little bit of everything. But of course you want to understand exactly how we got our water, because that's so important for life on Earth. And I think it's premature to say where we got it. We've got a lot of fascinating dynamical models that are telling us how to build the architecture of the solar system right now. But they don't couple with the chemical models of disks. And so I think what we need to do is look at the chemistry of the markers that could tell us where the water came from, whether it was the outer solar system, the asteroid belt, or in the inner solar system. So I think that's the state at which we're at. Now, of course, comets would have also brought other important components for life, such as organic compounds, because they certainly have a lot of rich organics on their surface. Now, the next question from Sarah is, what's my favorite thing about being an astrobiologist? Well, I think I somewhat addressed it in the introduction. I think the neat thing now is that I'm learning so many new things, and I'm tying together different fields. It's like being a kindergartner again. You know, one of the most rewarding talks I've had in the recent past was in being invited to go to a kindergarten class. And the teacher said, I was going to give a talk on planets in the solar system. She said, you're going to be here for 2 hours. Please prepare about 10 minutes worth of material. And I thought she was nuts. But the kids are so intrigued. They're asking millions of questions, and they have no fear about being judged. And so I think that's what's neat about astrobiology, because I can take what I know about comets in my specialty, and because I'm talking to people from different fields, I don't have the fear and embarrassment of asking the stupid question. And in fact, that leads to some fundamentally important questions that people from that community also aren't asking because it seems so stupid. A quick example is I was at a meeting in Iceland to talk about volcanoes. I was going to go there and get some field samples, and my colleague said, come to this volcano meeting. And I wasn't sure I would get anything out of it. Well, they were talking about pyroclastic volcanic eruptions, and I suddenly got an idea. I said at the end of the meeting, could I show you a picture of a comet? I said, here's the image of Tempel 1 from the Deep Impact mission. There's this flow feature on the surface that we didn't understand how it got there. And to me, it looks exactly like the volcanic flows you've been showing me. Is there any way these could be connected? Could we have a volcanic process on a comet? And could your models that you're running for the volcanoes on Earth apply to a comet? And so in the end, this is how we discovered that we could have a CO2 volcano on a cometary body on something really small where you don't expect volcanism. So that's what's been neat. Another question is from Kara. How large could comets have been in the early solar system? Talk about giant comets impacting Earth or Mars, incorporating water into the parent body. Well, we certainly do know that there were giant comets. We have evidence of these now. These are the sun gracers. There's a couple of families of sun-gracing comets. Particularly well-known one is the Kreutz sun gracers. Now, sun gracers are only special in that their orbits have a perihelion distance that takes them so close to the sun that they're effectively skimming through the sun's atmosphere. And there's been several thousand discovered on orbits that look like they all came from one giant body in the past, maybe 100 kilometers or so in radius. So we certainly know that there were large comets in the early solar system. Actually, one of those innocent kindergartner questions that was asked in one of my comet lectures that I'd never ever thought about was how many comets would it take to bring Earth's oceans? If we're talking about these giant sun grazers, it may only need a few hundred. If we're talking comets more like Hale-Bopp, many thousands of them, or generic comets, the typical comet size being a few kilometers, maybe 1,000,000. But even so, that's not that many given the population of impactors in the early solar system. Sarah's asking, how often do I do outreach and how do I balance research and outreach? Well, that's interesting. When I first got to UH as a young researcher, I had to start thinking about how to get money. And I had a student here that was very interested in working with me. So I was starting to think about writing my first grants, and an opportunity came about where NASA really wanted to have some opportunities to bring students into the outreach arena, and they were offering grants of $35,000 a year that was intended to be $25,000 to support a graduate student, $5,000 for an undergraduate, and $5,000 to run a teacher workshop. So I said, how hard can outreach be? So I wrote a proposal, and they liked it, but said, sorry, we don't actually have any money for that program. But then Keck Telescope stepped in and said, but wait a minute, we've just bought in to do extrasolar planet research. At that time it was called TOPS, toward other planetary systems. So they said, if you switch your entire topic to TOPS, then we will give you the funding for 3 years to do this. Well, and they said you have to do it on the Big Island. It certainly turned out that you can't do a big teacher workshop for 2 weeks where it's in residence for $5,000. So off I went into the realm of private fundraising to support these workshops. And I learned just how hard it can be to do outreach. It takes a huge amount of time. And so that TOPS program in my early years as a faculty member probably took me 2 full-time months per year to do. And I kept it up for about 10 years at that level, but now have gotten out of running those enormous workshops because it is such a time sink, but very rewarding. So now we build in outreach in other ways. I pay people to do the organization, and then we involve the scientists at a level where they're committing time to do science as opposed to also organizing the programs. I'd have to say right now maybe 10% of my time is still dealing with outreach, which is quite a bit. And you have to like doing it, and you have to find some benefit, because unfortunately still, when it comes to tenure and promotion, it counts, but if you did fabulously on outreach and teaching and had neglected your research, you probably don't move forward. Whereas if you do fabulous on research and have also done a good job on the outreach, it helps, but isn't the driving force. Another question here from Kara, how much water could have survived if comets had impacted magma? Well, it doesn't really matter what they impact into, because the impact velocities are so high that the impactor and the target material both vaporize. And there have been a number of scientists that have done simulations of especially things like the moon forming impact on Earth, which was a gigantic Mars-sized embryo that hit Earth. And those calculations show that, certainly you're going to vaporize everything, but the gravitational attraction of Earth is enough that you're not going to have escape of all the water. On the other hand, in the remnant debris field that became the moon, the water did escape from that because it couldn't gravitationally hold it. So Sanjoy is asking, what advice would I give to young women seeking a career in science? Well, yeah, it's been interesting. I'm a woman. I've taken a career in science, and I never particularly paid attention to the gender issues, although I know it's extremely important. I'd say learn early how to manage your time well. because you may end up having other activities that the men don't have that will draw your attention, issues like wanting to raise a family, although more and more this is becoming a male issue also. I would say I personally haven't encountered discrimination, although I am feeling, as I get farther in my career, certain pressures that I get annoyed with because of men. Often men have spouses at home that take care of things. I don't have that, not being married myself, and so I feel that sometimes I have additional pressures that the men aren't feeling. So I think one way that's helped me is to learn to become super efficient so that I can effectively do it all. One thing I have given up is I've elected not to have a family, and so I don't know if I'd be at the same place if I had because of the time commitments. So I think the biggest single piece of advice is to learn how to do what you do extremely well and extremely efficiently. Another issue I've noticed that seems to be different from colleagues at my level, men versus women, is the management skills. I think has been harder for women that I've noticed at this level, in part because we tend to be a little bit more emotional. I've seen men make executive decisions that are just absolutely brutal in terms of firing people, in terms of performance reviews, and I tend to spend a lot more time trying to fix the problem, to empathize, and maybe I shouldn't. Maybe that's a good thing, maybe it's a bad thing, but it means it takes more time out of my research activities when I'm dealing with that level of things in terms of management. Let me scroll through and see if there's questions I missed. All right, Kara's asked, what kind of information about the early solar system can we ascertain from comets that we haven't been able to due to lack of sample return? Well, one of the things that might be a marker of where the volatiles came from are the chemical fingerprints, such as isotope ratios. For example, deuterium to hydrogen ratio in water and other chemicals is a sensitive thermometer of where they condensed in a nebula. So if you have, for example, in cold regions in space, you get incredible deuterium enrichment because of ion molecule reactions that preferentially go in the direction of forming deuterium at very low temperatures. This will have occurred in our protosolar nebula also, and it will be a function of how warm the region was where you're forming the ices. Whether or not there's noble gases trapped inside of ice matrices depends very sensitively on temperature. You can get an order of 1,000,000 difference in the amount of noble gases in the range between 30 and 100 Kelvin. There's also a bunch of models that talk about self-shielding that the cosmochemists have been working on to explain oxygen isotopes that they see in the meteorite record, which involves preferential absorption of UV radiation depending on the isotope of oxygen in the CO molecule. So all of these different bits and pieces can give us clues as to where material formed. So in terms of the ices, a lot of these measurements simply aren't doable from Earth. We can't get noble gases from Earth. It has to be at ultraviolet wavelengths from space, and their abundance is so low, you actually have to be in situ to get enough gas to actually measure these things. So I think we've gotten samples in situ now from Jupiter family comets. We certainly have plenty of asteroids that we can measure in the laboratory. We've had the Cassini mission that flew past outer solar system. Enceladus got samples of its gas. The one area that's missing is sort of the outer asteroid belt where we're discovering there's a lot of water. So Julia's asking, she says, at the Astrobiology Winter School there's a problem with Earth water origins. What are some of the reasons the Earth is wet while the other terrestrial planets are relatively dry? Well, I suspect that Venus was wet, but of course it's got a different situation in terms of its runaway greenhouse effect. So I suspect Venus once did receive a lot of water, just like Earth, but it's lost it. Now, of course, Earth being wet, I wouldn't necessarily say Earth is wet. We don't actually know, to at least a factor of 3, maybe more, how much water Earth has. We can certainly measure how much material is in the hydrosphere, namely the oceans, rivers, streams, atmosphere, and that's about 1.3 ocean volumes of water. What we don't know as you go deeper and deeper into the Earth how much water the minerals are holding. And you can estimate it by looking at core samples, but once you get much deeper than a few kilometers, it's all theoretical. And there you can do laboratory experiments to look at how much water minerals could hold. You can look at seismic experiments that show velocity profiles that indicate there has to be water inside the Earth. And you can look at theoretical constraints that you couldn't have plate tectonics without significant hydration in the mantle. But all that being said, there are people that estimate we could have 10, 50, 100 oceans worth of water inside the Earth. But if you take some of the most reasonable estimates of 3 oceans or so, that's only about 0.1% by mass of our Earth being water. So whether or not you call that wet, it probably isn't considered very wet. Now Mars is a lot smaller. It certainly, we're getting more and more indication that it had a lot of water, and much of that may still be there in terms of it being frozen beneath the surface, but we just aren't having evidence of it there today because the atmospheric pressure is so low and the temperatures are low that we can't have surface expression of the water. So I hope that answered your question. Sanjoy is asking if I could talk about some future missions that will explore comets. Well, right now the Rosetta mission's in the news and very exciting. This was a mission that launched about 10 years ago to go to a Jupiter family comet, Churyumov-Gerasimenko, and the idea is to have both an orbiter and a lander that will arrive at the comet this August 2014 and spend a lot of time with the comet as the comet approaches the sun and begins to become active. Now they've just woken up the spacecraft. They had to put it in hibernation to save money, and it woke up in January as predicted, and so everyone was very excited with that, and the mission teams are ramping up for a very exciting mission. Now this was a European large mission, and so they have a lot of instruments. I don't remember how many. It's on the order of 20. They've got imaging cameras, they've got mass spectrometers, they've got on the lander things that can scoop up some material and analyze it. They have effectively a microwave experiment that can do some internal imaging into the comet. So this is going to be a really exciting mission once they get there and land. And as we are approaching the comet, I think it's going to be exciting also. In terms of other small body missions, you know, people will scream at me if I say we've got the Pluto Horizons, and that's just going to a really big comet in the outer solar system, trans-Neptunian object effectively. That will get there in the summer of 2015, and so that will be also an exciting mission. If I had a limitless budget, what comet and or asteroid would I visit and why? Well, I would actually go to the outer asteroid belt, and I would have that's effectively what we're proposing. We're trying to get to a main belt comet because it's one of the reservoirs of water in the solar system that we have not yet investigated. And because that reservoir, we believe, formed at that distance from the sun, it probably will tell us something about material that could have been easily delivered to Earth. So I would go not just to one main belt comet, but I would explore many of the asteroids in the outer main asteroid belt to look for evidence of hydration, to look for outgassing. I would certainly spend some time at Ceres. The Dawn mission is going there but it doesn't have the right sort of instruments to really explore the chemistry of Ceres. So I think I'd have a nice set of rendezvous in the outer asteroid belt. It would also be very interesting to explore a dynamically new comet. And what these are the comets that are kept in cold storage out in the vicinity of the Oort cloud, and then periodically nearby we pass close enough to a star that there's a perturbation that sort of nudges one of these guys into the inner solar system, and we see it as a brand new comet. These may be chemically different from the short period comets, and I think it would be fascinating to go to one of those. The problem is planning a mission to an object that you don't know is coming is very difficult. Sarah's asking, what do I think would be the most exciting discovery that could come from understanding the early history of water in our solar system? Well, I think this is really exciting in part because of all the discoveries of extrasolar planets that we have nowadays. We have something like 1,000 worlds in extrasolar planetary systems. Many of these have terrestrial planets that we're discovering, but it's getting harder to discover those that are in our traditional view of the habitable zone. So what if it requires some exotic mechanism to bring water to Earth, or to distribute water in the early solar system into habitable zones? Does it require an asteroid belt, for example? Does it require an Oort cloud? Or is this a common process that you would expect in any planetary system? So I think understanding how the volatiles and, as a consequence, the organic compounds got distributed has huge implications as to whether or not planets that now exist in a habitable zone could in fact be habitable, because if it requires some special conditions to get water to a world, then maybe habitable zone planets might not be inhabited by life. Random question from Kara. If we could somehow obtain it, could you eat ice from a comet? I wouldn't, because of the minor constituents that we do see in comet spectra. In fact, it brings to mind some of the early 1900s alarms that were given because it was known that Earth was going to pass through the tail of Halley's Comet in 1910. And people had just been starting to get spectra of comets. And when you look at a spectrum of a comet at optical wavelengths in the visible, you see a whole bunch of molecules, but these are fragments of bigger molecules, and what you tend to see are chains of carbon, so C2, C3. However, you see some nitrogen compounds, but the one that you saw most intensely was CN, cyanide. Now, this doesn't mean that cyanide is hugely abundant, but it's a minor component, and it just happened to be the brightest line because it's very efficient at fluorescing at these wavelengths. At infrared wavelengths, we know there's methanol, methane, ammonia. So I would suggest that just taking a bite of comet ice, it's going to have a lot of poisonous compounds in there, so I would not do it, even though it's mostly water ice. Sanjoy's asking if I could speak about some of the mentors I've had through my career. I think some of the ones that were the most important were probably two women. One was Dorrit Hoffleit. She was one of the preeminent female astronomers. She developed the Yale Bright Star Catalog. And I met her by virtue, it actually started with archaeoastronomy. In high school, I'd gotten a Earthwatch scholarship to go on a research expedition in Peru to do archaeoastronomy. And because that was such a fantastic experience for me, I applied for another research scholarship through Earthwatch. And this time it was for a summer job at the Maria Mitchell Observatory, which was the site of the first, it was the observatory where the U.S. first female astronomer worked. I got accepted to the program, and the year I was accepted was only the second year in which they'd even allowed women into this. No, the second year they'd allowed men into the program. And Dorrit Hoffleit was running this. She was near the end of her career, near retirement stage, and she was most unhappy that men were in the program at all. It was ruining her special program for women. So she took extra care with mentoring the women, and she was a really strong figure that taught me a lot about how to do science. And as a consequence of that, she had invited a young astronomer, Mattie, to help participate with the program. And Janet and I got on very well. And so when I was looking for a break between undergraduate and graduate school, one of the jobs I ended up getting was as a data researcher at the American Association of Variable Star Observers, where Mattie was the director. I'd also gotten some summer work with her. So she instilled a lot of good values about how to do science, some of the humorous side of things, and probably instilled a lot of the education and working with the amateur community values that I've gotten now. Kara's saying no cocktail parties on comets. Well, you know, when I ran it wasn't a winter school, but it was a specialized retreat in Iceland to look at the origin of water, where we had we had about 20 scientists from each of the main disciplines that would help us understand the issues related to origin of water. There we did have cocktail parties with glacial ice, because one of the things we did was also go out and do field work in terms of collecting some rock samples to get at deep earth water samples. As part of that field work, one of our team just had to have a huge chunk of glacial ice, and they stuck it in the freezer at the hotel, and every night we'd chip it off and have glacial cocktails while we discovered origin of earth water. So I'm told I should scroll up because I missed a question from Graham. Yes. He said, I met you in Santander a couple summers ago. I gave an interesting talk on how to inspire people from other cultures who want to explore space. Can you talk about what you think the human future in space will be? Well, I teach an astrobiology class, and part of my astrobiology class is space resources and human futures in space. I think that it's the next frontier. You know, much like the Wild West was the frontier in the 1800s, in part for resources, but in part for just the sheer spirit of exploration. I think the human future in space will also be in that spirit. I think there's going to be resources that will be beneficial to us on Earth that we can get from space. In particular, things like helium-3 as a fuel for nuclear power that doesn't have radioactive waste. I think we are exploring, humans are driven by exploration, and I think this is the next frontier. But it's going to be such an expensive enterprise that to be practical and to devote precious resources on Earth when we have so many pressing problems on Earth, it's going to have a specific benefit to humans on Earth in terms of resources, scientific discoveries, innovation. I think it will happen, but I think it will have to be economically driven, perhaps by private enterprise. Sadly, if it's going to be government driven, I think it will have to be because we are fearing something like the space program in the 1950s and 60s was driven by the Cold War. I think that's the way that government will invest enough to do it right. For humans to understand that it's important, I think there has to be either that or profit. I hope it happens, but it may not be in our lifetime. Early career astrobiologists. I think when I've gone to the DPS meeting and I've gone to the early career night a lot, I think it's getting harder and harder to get research grants to support young people. And so I think early career in any field, but especially in astrobiology, you have to make a name for yourself, and part of that is getting yourself out there. You need to give really good talks. You need to engage in the public outreach, because that's where people understand that you're a person that's doing interesting science. You of course need to do compelling science, and I think part of doing compelling science, at least in my end, it was being very detail oriented. I think you either have scientists that are brilliant at the back of the envelope or really good at details. I think presenting yourself with quality at all times is really important. So partly for that reason, I always advise my students that I don't want to see them go to a meeting and give a poster. I'd rather have them go to a meeting and give a really nice oral talk, because there you have 100 or 200 people in the room seeing who you are and how well you present yourself. Whereas at a poster, you draw the people that are intensely interested in your poster, but it may not be that many folks. Of course, you have a lot more opportunity to spend quality time discussing it with people, so this is partly my personal feeling. But I think presenting yourself with quality and asking questions in meetings gets a lot of the senior people that may want to bring some new blood into the community just a heads up as to who you are. And it really is the squeaky wheel that gets the attention. In terms of the NASA Astrobiology Institute, people worry as a young person how to get into astrobiology. Can I be really good in one field, but do I have to be really good in a whole bunch of fields to be successful in astrobiology? You absolutely have to get a degree in something and be really good at it. But the more you know how to draw the connections between fields, the better you will be as an astrobiologist. And so this means understanding the vocabulary, understanding some of the big picture questions. It doesn't mean being a specialist in that field. And you can help people understand your science by, at any big meeting, not getting too heavy in the jargon, but explaining it in a clear way that's accessible to everybody. So Julia, have I managed to hit everybody's questions? I'm scrolling through and it looks like I've caught most of them. See, the idea of glacial cocktails was people were impressed. The hotel staff were impressed too. They couldn't believe that we were lecturing until 10 or 11 at night. Well, you're welcome. This was very interesting. I think the secret to having a really good interdisciplinary meeting was isolation. We picked a tiny little town in Iceland that had a hotel with 21 rooms, and we filled the 21 rooms with our people, and the town was so small that it had nothing else to do. So that meant our group stayed in-house, and in our off time they were discussing science. And that meant that you could make some real progress, as opposed to going to a meeting where you can waft off and do something fun in the city or go to your room and watch TV. Yeah, there were no phones or TV at this hotel either, so you get into some very interesting discussions late night with your glacial cocktails.